I once again welcome you all to the lecture series on main group elements. In my previous lecture, I was discussing about chemistry of group 16 elements and I was discussing about oxyhalides. Let me continue from where I had stopped. Oxyhalides of sulfur, selenium and tellurium are very important and they have general formula where E equals sulfur, X equals F and Cl, and where E equals selenium, this is with chalcogen in its plus 6 oxygen state. Oxychlorides with chalcogen in its 4 oxygen state are also known, they are EOX2, and here again when E equals sulfur or selenium, for halides such as fluorine, chlorine and bromine are known. That means SOCl2, SOF2 and SOBr2 are known. All sulfuryl, so they are called sulfuryl halides and they are thionyl halides in case of sulfur. So, sulfuryl and thionyl halides and their selenium analogues are powerful halogenating agents and find application in inorganic as well as organic chemistry. For example, in the preparation of chlorides from alcohols and anhydrous metal halides, these compounds are widely used. Let me write a couple of examples here. Take a typical alcohol and treat with thionyl chloride SOCl2, it forms RCl, and in transmetallic chemistry for the preparation of anhydrous metal halides for their utility in organometallic chemistry, one can generally treat the hydrated salts with excess of thionyl chloride. So, this is where the utility of sulfuryl and thionyl chloride comes into the picture. So, let us look into a couple of questions here. Predict the shapes of molecules SOCl2 and SO2Cl2, and simply if you look into SOCl2, that is in plus 4 state. So, we have here in this case 3 bonded pair and 1 lone pair, whereas in case of SO2Cl2 we have 4 bonded pairs. So, this has a pyramidal structure, trigonal pyramidal structure, whereas SO2Cl2 has tetrahedral structure. Okay. So, oxyacids of sulfur, selenium and tellurium are known. A wide range of oxyacids and or their anions are known for group 16 elements. Sulfur and selenium show coordination number up to 4, while tellurium tend to be 6 coordinate. Compounds with SS bonds are also quite known. Sulfurous, selenous and tellurous acids having composition H2SeO3 . So, here when sulfur is there, it is sulfurous, when selenium is there, it is selenous, and when it is tellurium, it is called tellurous acids. SO2 is very soluble in water and dissolves largely without reaction, forming an acidic solution known as sulfurous acid, that is H2 SO3. The free acid has never been isolated and is either absent or present only in trace amounts of SO2 solutions. SCO2 and TiO2 behave very similarly, but are less acidic than H2SO3. A solution of EO2 where E equals sulfur, selenium or tellurium in aqueous hydroxide solution gives the corresponding EO3 2 minus or HEO3 anions. For example, SO3 2 minus plus S gives S2O3 2 minus. Okay. Thiosulfate is widely used in redox titrations involving iodine. In this reaction, tetrathionate, that is S4O6 2 minus, is formed, which contains a chain of 4 sulfur atoms. Tetrathionate is a member of unstable sulfur bridged polythionates of composition okay. So, where N can be, so very interesting, N can have anywhere between 0 to 22. How it reacts with iodine can be seen here. For example, I2 when it is treated with S2O3 2 minus, I minus is formed through the formation of tetrathionate S4O6 2 minus, and this I3 minus reacts with S2O3 2 minus to give 3I minus plus S4O6 2 minus. So, I3 minus anion is most commonly encountered during redox titrations involving iodine, where an excess of iodide ions is added to convert any iodine formed to the soluble I3 minus. The solubility of I3 minus is dependent on the size of the cation M plus we are using here. Okay. And to precipitate I3 minus ion from solution, large cations such as tetramethyl ammonium or tetraphenyl arsonium are preferred. Okay. The cation also has a marked influence on the structure of the anion. The smaller cesium plus ion distorts the I3 minus ion, whereas the larger cation such as triphenyl arsonium does not. So, as a result you can see the structure will be little bit deformed. For example, if we look into PH4AS I3 minus and if you just look into the I3 minus here, I3 minus are symmetric, II distance is 290 picometer, very symmetrical. If you look into I3 containing a smaller cesium cation, it is distorted. So, in this case, so this is 283, whereas this one is 303 picometer. So, this is unsymmetrical and this is symmetrical. Okay. So, that indicates how cations have influence on the structure of anion. So, oxoacids and their salts resemble the complicated system of phosphorus. There are structural analogues between sulfates and phosphates, although fewer condensed sulfates are known. So, redox process involving sulfur oxoanions are often slow, and thermodynamic data alone do not give a very good picture of their chemistry. Compare similar situations for nitrogen and phosphorus containing oxoanions. So, selenium and tellurium have a relatively simple oxoacid chemistry. Other sulfur acids and their anions, one can see, for example, sulfuric acid H2SO4, one of the OH groups may be replaced by a hydroperoxo group to give monoperoxo sulfuric acid, or OH group can also be replaced by a halogen or NH2 or NH, or by an organic group, say methyl group. So, that means in sulfuric acid, if we can replace OH group with other groups, we can get different sulfur acids. Thiosulfate anion has the same structure as sulfate, but with an oxygen replaced by a thiosulfate. One of the O group is replaced by. So, for example, so this is sulfate. In thiosulfate, basically what happens? So, this is, so one of the oxygen is replaced by sulfur. Thiosulfate ion is a very good complexing agent for silver plus ions, and sodium thiosulfate is used in photography for removing unchanged silver bromide from exposed photographic film. So, now nobody is using photographic film as we have entered into digital era. However, one should know how photographic films were developed. For example, AgBr, when it is treated with sodium thiosulfate, it was forming a silver complex So, that means unchanged silver bromide was essentially removed using sodium thiosulfate. So, most oxidizing agents including chlorine and bromine slowly oxidize S2O3 to SO4 thiosulfate into sulfate, and thiosulfate is used to remove excess of chlorine in bleaching process as well. Selenous acid H2SeO3 may be crystallized from aqueous solution of SiO2 and gives rise to two series of salts containing HSeO3 minus and SeO3 2 minus ions. I will show you some of the sulfuric acid derivatives here. As I had mentioned, if we replace OH with chlorine, we get chlorosulfonic acid. For example, this is sulfite anion, and this is from sulfate. As I mentioned, one of the oxygen is replaced by sulfur, it is called thiosulfate S2O3 2 minus, and then this is sulfuric acid H2SO4, and if one of the OH group is replaced by chlorine, it is called chlorosulfonic acid, and similarly if we replace one of the OH group with NH2, it is called amidosulfonic acid, and OH is replaced by methyl group, it is called methyl sulfonic acid, and this is dithionate S2O4 2 minus, and this is pyrosulfite S2O5 2 minus, and it is dithionate S2O6 2 minus, and this is tetrathionate having 4 S in a chain having SS linkages, it is S4O6 2 minus, and 2 minus can be seen here. So, let us look into the preparation of some of these compounds, how these compounds are prepared. For example, treat SO3 with HCl, it gives chlorosulfonic acid, or one can also, so I am writing in a different way. This is essentially sulfuric acid. I am writing in a different way to show the functionalities here. This is when it is treated with PCl5, also it gives ClSO3H plus POCl3 plus HCl, and chlorosulfonic acid, when it is treated with SO3, it gives H2SO4 plus S2O5Cl, and sulfomic acid is produced industrially in two stages: urea with a mixture of SO3 and H2SO4 or oleum. For example, this is urea NH2 CONH2. This is first treated with SO3, give NHSO3H, and this one on further treatment with H2SO4 forms 2H3NSO3 plus CO2. Okay. So, in this way approximately 1 million tons of amidosulfomic acid is produced every year, and this chlorosulfomic acid is useful in detergents and also as chemical intermediate. For example, ROH plus ClSO3H gives ROSO3H plus HCl. Okay, so one can make here methyl or alkyl. An early synthesis of saccharin begins with the reaction of toluene with chlorosulfomic acid to give ortho and para toluene sulfonyl chloride derivative, and this one is so prepared for the first time in 1879. Okay. Oxidation of the orthoisomer gives the benzoic acid derivative, which is cyclized with ammonia and neutralized with a base to afford saccharin. Chlorosulfonic acid has been used as an anti-contrail agent in Rayon model 147 reconnaissance drones and to produce smoke screens. Okay, so let us look into group 16 halides. In contrast to the trend found in earlier groups, the stability of lowest oxidation state, that is +2 of the central atom in the halides of the group 16 elements, decreases down the group. Oxygen difluoride is highly toxic and it is prepared by the reaction of NaOH and F2. So, although OF2 is formally the anhydride of hypofluorous acid HOF, pure OF2 can be heated at 470 Kelvin without decomposition, but it reacts with many elements at or slightly above room temperature to form fluorides and oxides. So, oxygen, interestingly, oxygen forms 6 fluorides, which are rare examples of compounds with oxygen in positive oxygen state. One should remember oxygen being the second most electronegative element can exist in plus oxygen state only when it is reacted with fluorine. It is interesting to know that we have several fluorides of this type having up to 6 oxygen atoms in a chain. For example, OF2 is known, O2F2 is known, O3F2 is known, O4F2 is known, O5F2 and O6F2. Okay. And they can also be prepared by treating sodium hydroxide with fluorine. If you take O2F2, analog of hydrogen peroxide, and it is treated with 2 equivalents of PF5, phosphorus pentafluoride, or BF3, it gives O2 plus and PF6 minus ion salt plus F2. So, by direct oxidation of O2 using PTF6, which one can prepare O2 plus cation. For example, O2 plus PTF6 gives 2 O2 PTF6. In fact, this reaction led to the isolation of first noble gas compound by Bartlett. I will be discussing about the group 18 chemistry, especially that of xenon and krypton, when I proceed to the chemistry of group 18 elements. The structures of some of these oxyfluorides can be seen here. One can also write like this. And here this angle is 109 and this OO bond distance is 122 picometer and this OF bond distance is 157.5 picometer. Okay. The fluorides of sulfur such as SF4, S2F2 can be prepared from the reaction of SCl2 and HgF2 at elevated temperature. For example, sulfur chloride, when it is treated with fluorinating agents such as sodium fluoride in acetonitrile at 350 Kelvin gives SF4 okay. So, both SF4 and SF6 are highly stable. Disulfur difluoride exists as 2 isomers, that is S2F2 and F2S double bond. Okay. So, I will write the structure, these 2 structural isomers. This angle is 108 and this is 189 picometer and this Fs bond distance is 163.5 picometer. Other structure is and here it is 160 picometer and here it is SS bond distance is 186 picometer and here FSF angle is 92.5 degree, whereas SSF angle is 107.5 degree. most of the people who have learnt VSCPR theory are quite familiar with the structure of SF4, and also I had discussed the structure of SF4 while dealing with the structure and bonding concepts in earlier lectures. However, let me write the structure of SF4 here. Okay, see this is like seesaw type structure, and also SOF4 has trigonal bipyramidal structure. Okay. Among the sulfur fluorides, SF6 stands out for its high stability and chemical inertness. It can be made by burning S in fluorine and is commercially available, widely used as electrical insulator. The preparation of SF6 from S and F2 produces small quantity of S2, F10 as well, and the yield can be optimized by controlling the reaction conditions. Molecules of S2, F10 have the staggered structure. It disproportionates when heated and is a powerful oxidizing agent. For example, S2, F10 when it is heated to 420 Kelvin, it forms SF4 plus SF6. If you are curious to know the structure of S2, F10, here it is. Sulfur forms a wide range of halides, particularly with fluorine in oxidation states ranging from low fractional positive oxidation states to group oxidation state of +6. Monohalides such as S2, X2 have structures similar to H2O2, but S2, F2 has been found to exist in two isomeric forms that already I showed you. Besides this, S2Cl2 and S2Br2 are the smallest members of a series of chloro and bromosulfanes of the type SNX2. Sulfanes with up to 8 sulfur atoms in the chain with SS bonds are known, very similar to HSNH, called as polysulfanes. Sulfanes are formed by direct combination of the elements. Quickly let me write SC8 plus 4Cl2 gives 4S2Cl2. Only stable species is bent SCl2, which disproportionates to give S2Cl2 and Cl2. So, SF2 is even less stable. For example, SCl2, it disproportionates to give S2Cl2 plus Cl2. Sulfur 4 are restricted only to SF4 and SCl4, and in solid state SCl4 is thought to exist in ionic form, such as SCl4 is thought to exist in the form of SCl3 plus and Cl minus. Let me write quickly the hydrolysis reaction of SF4. It gives SOF2 plus 2HF, SF6 Okay. So, SF6 is kinetically inert because it is coordinatively unsaturated, having 6 coordination number, having octahedral geometry. However, Under drastic conditions, it undergoes hydrolysis and SF bonds can be broken. Under normal circumstances, SF6 is stable. So, let me stop at this stage and continue in my next lecture remaining portions of the chemistry of group 16 elements. Thank you very much.